Hi, everyone.
Hello.
Welcome, and thank you for having us. My name is Kenny Bastani, and this is Jakub Pilimon. If you're here to hear about state or events. Now, that is a very ambiguous title for a presentation, but we'll get to that. So my name's Kenny Bastani. I'm a global CTO at Pivotal. I wrote a book called Cloud Native Java with Josh Long, who happens to be at this conference also. So I think it's like the first time that Josh and I have ever been at the same conference speaking together separately. So that's interesting. Anyways, so what I do at Pivotal is I get to go around the world and I get to talk to our customers. I get to work with our field, our platform architects all across the world to make our customers successful. Now, before that, I was on the Spring team as a Spring developer advocate, which is what Jakub is.
All right. Hello, everyone. So I work at Pivotal too. My name is Jakub, and that's interesting because my current position is Spring Developer Advocate, which is Kenny's former position. I actually took his job, but you know, he wrote a book, so
They couldn't fire me.
yeah, they couldn't fire him. So what do you do with people who you cannot fire? You just promote them, and now he's global CTO.
It's called Peter's Principle.
Yeah. So I'm the Spring Developer Advocate. I have a Twitter account. I have a blog. I run a pet project which is called TDD by Examples. I do it with my friend. So if you want to collaborate with us, you can find us at GitHub. There's plenty of fun work to do together. So feel free to reach to us.
I have a GitHub too, but I didn't put it on the slide. We'll get to that at the end. All right, so here's our agenda for today. We're going to split between the two of us. I'm going to start out talking about event sourcing, a history. So who here has heard of event sourcing? Wow,
Nice.
that's good. That's really
quite
good.
a few people.
Now, who here knows the origin of the term log in computer science? See, that's a tough one. So we're actually going to go over that too because it's very relevant to event sourcing because what does event sourcing use? A log, right? So we're going to talk about that. Then we're going to talk about Apache Kafka and the immutable log, the source of truth, and how that works. And then Jakub's going to talk about event-driven microservices. I'm going to talk a little bit about Spring Cloud Stream and Apache Kafka. And then we're going to go through a reference architecture if we have time. So let's hopefully have time.
I hope we'll have time.
All right, cool. So event sourcing, there's a mystery and a history behind the idea of event sourcing. Now, I'm a bit of a historian of computer science. Writing the book Cloud Native Java, I really enjoyed looking at the history of Netflix. And so I had to watch hours, tens of hours, hundreds of hours of videos and put together a timeline and figure out exactly what happened so that I could write the chapter on Netflix and cloud native applications. And so I took this further and I did it with event sourcing. And there's an origin story here. Now, Martin Fowler, back in 2006, he defined event sourcing on his blog, and this is the first instance that I could find on the internet. And he said this. He said, event sourcing ensures that all changes to application state are stored as a sequence of events. Not only can we query these states or events, we can also use the event log to reconstruct past states. We can determine the application state at any point in time. We do this by starting with a blank state and rerunning the events up to a particular time. Now, I needed to go back further because event sourcing as a term is very interesting. And this is a very difficult notion to understand just by reading that blog post. Now, a lot of people today argue about event sourcing and CQRS on the internet. And so I really wanted to figure out what's a better metaphor for all this? How can we make it simpler? Now, the question I asked myself was, did Martin Fowler invent event sourcing? Now, this goes back all the way to the 1800s. Edgar Allan Poe actually said this in one of his poems. Now, Edgar Allan Poe is not a computer scientist because if you notice the date on here, that's before computers. And so, but what he said was this. He said, we appreciate time by events alone. For this reason, we define time, somewhat improperly, as the succession of events. But the fact itself that events are our sole means of appreciating time leads to the erroneous idea that events are time, that the more numerous the events, the longer the time, and the converse. And so that's a lot like the definition of what Martin Fowler said. Actually, it gets more eerie than that. That's probably maybe a loose connection, but I'll ask the question to you all. Did Edgar Allan Poe invent event sourcing?
He was a poet, right?
He was a poet.
I think it was Franz Kafka who invented event sourcing.
It might have been. No, so LOL no. Okay, so the term in computer science for log actually came from the 15th and 16th century. So even going further back, event sourcing goes back more than, I think, 400 years. When Portuguese sailors, when they wanted to cross the ocean, they needed to measure the speed of their ships more accurately. Now, the chip log is where we get the term log in computer science. And how it works is this. We have an ocean, and we have a ship, and we have something called a log reel. It's a lot like a fishing reel, and it's wound by a small rope with knots that are tied at equally spaced intervals. Now, you'll have two sailors, maybe it's me and Jakub, and what you'll do is you'll throw this underwater parachute out, and that's going to create drag, right? So that's going to unwind that reel, and more of these knots are going to come out of that rope. Now, at the end of a time period, let's say 10 minutes, what they're going to do is they're going to have the second sailor reel in that log while the original sailor holds onto the rope and counts the number of knots. So let's try this.
All right.
You go ahead, you reel it in.
I'm doing my job.
1, 2, 3, 4, 5, 6, 7, right? So there's 7 knots on this rope, so that would be 7 knots every 10 minutes. And so they were able to measure the speed that they were traveling pretty accurately using something that looks a lot like event sourcing using a chip log. Now, the Poe connection is interesting. So how did he come up with this idea of events in time? Now, Poe was obsessed with the idea of event sourcing for much of his life. But in his time, things were commonly measured using a form of event sourcing, right? So the knots on the log line for measuring the speed of ships, that was the way that they measured things. And so event sourcing essentially before computers was the way that things were measured. Now, most software, well, good software is built on good metaphors. The problem is we've forgotten the metaphors and the meaning. Now, in another poem called Marginalia, Edgar Allan Poe in 1849 said this. He said, "Space is precisely analogous with time. By objects alone we estimate space, and we might as rationally define it, the succession of objects, as time, the succession of events," and that is event sourcing. That's the definition that Martin Fowler had. And so I thought this was very interesting. And so if you really look at that chip log, you can see that Edgar Allan Poe, not a computer scientist, he was inspired by the way that these Portuguese sailors measured the speed of their vessels as they crossed the ocean. And so what aggregation is in event sourcing is that it takes causal events across space and time, and it summarizes it into a single object that's easier to store and communicate in memory.
The single object here is the speed of our boat, right?
Exactly.
Cool.
Now, all great software is built on great metaphors. Now, all of these words, I think I dumped them on an airplane, I dumped them on there in about 10 minutes. And these are the words that people really don't argue about online, right? We don't argue about these. We don't go to conferences to learn about desktops, right? Or maybe tablets, I don't know. But we certainly do about platforms, but we don't really argue about their meaning. It's very well understood what a desktop is. Now, these metaphors mean something. And there's an underlying abstraction to our own humanity, and it has an intimate connection to this virtual world we're building, right? So there's an abstraction in the virtual world that very much matches the metaphor in the real world. Now, the desktop computer replaced actual desktops by replacing the abstract functionality of an actual desktop, right? And then the virtual machine replaced the server by virtualizing the abstract functionality of the hardware. Now, we just keep on doing this over and over again, and we get a very confusing stack of abstractions. So ultimately, it's hard to keep track of all these layers, right? At some point, things become confusing, and then we give something a bad name. So we get lost in abstraction. And so all confusing software is built on nonsense. Things like serverless, middleware. Would you argue about microservices?
So you're
online?
saying serverless or microservices. These are nonsense?
Would you argue about serverless online?
Yes.
Because there's servers, right?
Yeah. So it's like there are no servers.
Does it make sense? What about an ESB?
I'm way too young to understand ESB.
That's very true. What about NoSQL? Which database should I use?
NoSQL?
What does NoSQL mean?
It's like without SQL, right?
Not only SQL.
All right.
Yeah, see?
I'm way too young to understand NoSQL.
SOA, anybody? Would you argue about that? What about DevOps?
This one I know. My boss told me what DevOps.
That's very appropriate because I think he created it. So I'm not saying that microservices, DevOps, and serverless are, in fact, nonsense. They're not. They're very valuable things. The problem is that they're not metaphors, not good metaphors. They're not easily describable. So serverless, because it says serverless and it has servers, we end up fixated arguing about that as opposed to talking about what serverless does. And so we waste a lot of time doing that. We go to conferences to learn about it just because the word itself doesn't make sense. So I'm not saying that metaphors make good ideas more durable to so I'm saying that metaphors make good ideas more durable to nonsensical interpretation. I got to make sure that Bridget gets that photo. So this is a log, right? This is also a log, right?
I know this log. I'm familiar with this one.
That's a very familiar log.
Yeah.
What about, you know that log right there?
Yeah. It doesn't differ, right? Because from this log, you could actually calculate the age of the tree.
Yeah,
right?
how would you do that?
By counting the things in here.
Yeah, that sounds like event sourcing, doesn't it?
So it's a log.
It's a log, yeah. Cool. All right, so Apache Kafka. Now, I'm not going to go through the full everything about Apache Kafka because we have a lot more content and we have about 30 minutes left. But I'm going to talk about the abstraction behind it and why we would use it. Now, Apache Kafka is the immutable log as a source of truth. That's the idea. It's that your events are going to be stored on a log, and that's going to be your system of record as opposed to what I call graffiti, which is your database, where an individual field is continually overwritten, and you have no history of it, right? So you're just going to go ahead and paint over the same status field, like an account, for instance, and its status. Now, we have these actions that users take on a website, like e-commerce website, right? So I'm going to add an item to my cart. That's an action. And that's happening in time, right? So each one of these knots on this log line here represents an action, and we can rerun these things to generate the current state of the system. Now, Apache Kafka uses that as an abstraction, right? So that log line there at the bottom, that's going to be our messages that we send to our topic, and that topic is going to store these messages in order. Now, we can rewind and replay this log to come up with the current state of the system, or one object that's easy to store in memory. So this is the same thing, but it's way before software, right? So this looks awfully like this, right? 500 years ago.
This is Kafka 500 years ago, right?
That's right. Yep. Or this, right? So actually, if you start to think about it, event sourcing is kind of used everywhere. Now, here's a GIF, right? And so each one of these frames is happening in its exact order. And the result is we get one object that is an animation.
So you're saying the materialized view is that this video?
Exactly.
It's based on the events, right?
Right. So these events, each one of these frames represents this materialized view, and we get an animation. So event sourcing, just to kind of summarize what it is that aggregates can be used to generate the consistent state of any object. It also provides an audit trail that can be replayed to generate the state of the object at any point in time. So you also get a TARDIS or a time machine as well with it, because you can rewind and you can look at the behavior of your users at any point in time, which is very useful. It also provides the many inputs necessary for analyzing data using event stream processing. So if you think about it, you get the added benefit of being able to analyze this behavior and run machine learning on all of these events and make predictions about your users, right? So you can actually make recommendations about which products that they should buy. Now, more importantly, for microservices, it enables us to do something called a compensating transaction. It allows us to roll back events that led to an inconsistent application state. Now, since we have the log, we know what happened, right? So we can do root cause analysis, and then we can create something called a state machine, which will add more events to that log to bring the system to a consistent state, which means that Jakub doesn't have to get up at 3 in the morning to go and fix the system, right?
Yeah, I don't want to be on pager duty, you know?
That's right. Right? So why aren't we doing it everywhere? Wait, who's doing event sourcing today? Just curious. 1,
Nice.
2, 3. All back there. Why are y'all back
Over
there?
there, too.
Yeah. So that's interesting. So why aren't we all doing it today? Why isn't this done everywhere? It seems like it makes sense, right? And that's because storing state as an immutable log of events for domain data did not make sense in a time BC.
There was no Kafka back then, right?
Kafka. BC before cloud. Now, what's the difference between the cloud and before? Now, before cloud, we had to manage our servers physically, right? You had to manage your own servers. Now, you have a limited amount of capacity, right? So you don't want to store every single event in your database because you're going to run out of disk capacity. Now, what happens when you run out of disk space on a database?
It doesn't work anymore.
You have to get up at 3 a.m. and fix it. Yeah.
I don't want to do that.
Nope. So you want it to be highly available, and you want it to be automated, and you want to be able to add space as you need it. Now, Apache Kafka has that ability, right? So when you run it in the cloud, you're going to have more capacity, which allows you to store all of that event data, and you can build an architecture that supports it. Now, the big difference here is that we used to have a database that we managed, right? And we didn't want to store too much data in there, and that's why we would have a relational database that we would just graffiti paste over individual fields. But now what we can do is we can have an event log, and we can derive state solely from the events alone. And so we get this time machine. So we can rewind and replay, kind of like a VHS. You were too young for VHS, right?
No, that I remember.
Okay, good. And so this looks awfully similar to how highly available databases run in production, right? So in this example, which is another metaphor, I have a zipper. Now, each one of these zippers represents one database. Now, I have a primary database, which is the zipper that's zipped all the way up. And then I have replicas, replica A and replica B, which are eventually consistent. Now, to generate the primary, a replica, an exact replica of it, all you have to do is pass the transaction log to another node and zip up those transactions all the way to the top, and then you have an exact replica. And that's what eventual consistency is. When all of these zippers are tied all the way up, then your system is consistent. But at this state, replica A and replica B are not consistent with the primary.
So how does it relate to transaction log or write-ahead log, you know, the thing in the databases?
That's exactly what this is. This is a transaction log. A write-ahead log is just in memory, and then eventually it writes it to disk. But
all right.
So this is just an abstraction, a good metaphor. All right, so let's talk about Spring a little bit, or what we have in the Spring ecosystem that allows you to do this. So we have Spring for Apache Kafka. Now, this is a project that's going to wrap the Kafka APIs. Now, we have two Kafka APIs. We have the Kafka Streams API, which I call the Kafka Screams API, because sometimes I want to scream at it. But we also have the Kafka Messaging API. And these are two different APIs that you're going to use for two different purposes. Now, the Kafka Messaging API is a message broker. So you can send messages along a channel, and you can send them to a topic on Apache Kafka. Now, the Kafka Streams API you can use to aggregate, to rewind back in time and regenerate the state of any object. And you can do joins, and you can do all kinds of things with it now. Now we have Spring Cloud Stream as well. Now Spring Cloud Stream is strictly for messaging, and this is where it gets a bit confusing, because Spring Cloud Stream is kind of like a swappable binder for different message brokers. And so you can support Apache Kafka, RabbitMQ. You don't have to change the programming model.
You know,
right? And more, right?
That's why I got your job, because there is more.
There's
not only Kafka and RabbitMQ. It's we have Google PubSub, we have AWS Kinesis. So
what about Azure? Do we have anything for Azure? We got to figure that out. Right?
Yeah, we have to check.
Get on the game, get on the ball. All right, so now we're going to do the handoff. I'm going to hand off the box.
So I'm the one with the box?
I'm definitely the fatter guy, for sure.
All right, I'm holding the box.
Okay.
Thanks for giving me the box.
Yep.
All right, so thanks for teaching me all of this stuff about event sourcing, but how does it really apply to microservices and event-driven architectures? Because we are here at Vox Days, microservices, right? So the story was pretty nice and useful, but I think we can try to relate that to event-driven architecture and microservices, right? So what's the main problem when it comes to distributed data and microservices, right? There are no foreign key constraints between microservices, and that's the ultimate problem that we face when it comes to distributed data and microservices. Each microservice owns its own database, and I cannot have like foreign key constraints between them, right? But yet, we have this domain graph. So each particular domain, even a simple one, can be divided into smaller chunks, right? And this is actually what domain experts see when they think or when they talk about their domain. If they were to draw a picture of the domain, probably it would have been something like this. So we have address, we have shipment, we have inventory, we have warehouse product catalog, right?
Right. So this is like the business logic of the application, right?
Exactly. And yet, this is the business logic, but we have to somehow apply this to our technology stack, right? So we have to, for instance, somehow persist this business logic somewhere.
Right.
So
how do we do that?
What we do, we do this, right? So we have our graph of domain, and then we try to apply it to our relations, tables, I don't know, columns, constraints.
So like a relational database.
Like relational database. And
who uses a relational database?
I'm using relational database.
Who has to change schemas based off of business requirements?
I do that a lot.
I do that a lot too.
Yeah.
And what is that called?
I think it has a name. It is something like impedance mismatch, I would say.
That's exactly right, yeah.
Because we have this problem space, and our domain model applied perfectly to the problem space, but now we have to somehow translate it to our solution space, and the solution space may not be a good fit always for all the things that are there in the problem space, right?
It definitely isn't.
So we have this impedance mismatch, but yet it can even go worse, right? Because we distribute that right now.
So we've actually gotten worse with microservices then, you're saying?
Yeah, I mean, with this, yes, because there's no foreign key relationships between your data. Let's say you have this catalog service, and then you have inventory service, right? So in catalog service, you can check how many products or what products you are actually able to buy, right? Like, have you bought something recently?
I did. I bought a shower head on Amazon. It's one of those fancy rain shower heads. It was, you know, I thought it was really cool.
On Amazon?
On Amazon
it's
Prime.
It's a bookstore.
Yeah, have you heard of it? I know we're in Europe.
Yeah.
It's in Seattle, very small.
So they sell something else then?
Oh yeah. So what ended up happening is that you know, it never came. It said that it was delivered, but it never was. And I was kind of curious, and I went to their help page, and it said just wait. And I waited, and I waited, and I waited.
But
and
it will be eventually consistent.
But it never came. And so I called support, and they said, we sent it to your address. And I was like, you did not. And so then I kind of figured out, I put it together. I was like, oh, I'm in a community with similar addresses. And so I went and I knocked on every door, and I found my shower head. And so I blame that on microservices.
Because they didn't have like foreign key relationships, I guess.
Yeah.
So there is the product catalog, right? And there is the instances of products in the inventory database. And you cannot have like relationship because there are two different microservices. And one of them is MySQL, the other one is Neo4j, so it doesn't even make sense, right?
Exactly.
So what we do, because after all, we have to answer this question, like I would like to have this distributed join across multiple microservices, right, to answer a question. And the answer is partitioned between several parts of my application. So part of them is, part of the answer is in the count, the other one is in order, and the rest is in the address, right?
And so the whole point of this is I want to ask a question, right?
Yes,
of my
what's your question in this case?
Find my orders by address or find address by order.
And it can be more complex, like it can involve like 10 of them or maybe 5 of them or 50 of them.
And you have to go across the network for all that.
Yes.
Yeah, that's
so
going to be
slow,
really, yeah,
right?
it's really slow. It's not going to meet the SLA, I don't think so.
And you would be unpaid duty again.
Yeah. So how do we optimize? How do we get better?
But this thing is the easier part, you know, because these are queries. Yeah. So queries can be repeated. They are safe. They don't change the state of your system, so you can repeat them safely.
Okay.
Right?
Yeah.
You can rearrange the order. It doesn't matter that much, right?
I can call any microservice and read, and I'm not going to mess the system up, right?
Hopefully.
Okay. Cool.
Hopefully. Okay. But then you have writes. So things that actually change the state of your system. Right? So most probably in your case, you would have wanted to change the address of your order from Amazon, right?
Yeah.
In this case, you have again, the order service, account service, address service, and yet you have to go and change the address in the order because that's where the orders are, but also in addresses. And how to do it in an atomic fashion. Like in monolithic application, it was super cool and easy because we had this thing called transactions, right?
Yeah.
You're familiar with transactions, right?
I am, yes.
So it's either 2 of them or nothing, and here I cannot do that. And two-phase commit is not an option because, you know, distributed managers, there are single point of failures, and it will be very, very slow.
Very brittle. And the network fails a lot, right? Yeah.
Yes.
Yeah. And so then we're going to end up having an inconsistency, meaning that we'll have an update somewhere, and then we won't have an update somewhere else. And then the system's inconsistent, and I don't get my shower head.
Well, we have to solve that.
Yes. How do we solve that?
So we have this thing called microservice joins. So coming back to our graph of domain, right? It looks like this. let's say our microservices are organized using domain-driven design concept. We don't have time to cover this in details, but let's assume that each microservice owns the data related to one bounded context, right? But then, again, you cannot own domain data from two different bounded contexts, right? You cannot do that, but you have to answer these complex joins, which span across different microservices, right?
So we have to do a distributed join,
Or
which is slow, right?
or maybe there's another option, but wait for it, okay? Yeah. And then, of course, you cannot do distributed transactions for writes.
Yeah, that's a very bad idea.
So what you can do and how it can be solved. Have you heard about CQRS?
Who here has heard about CQRS? Who has argued about it on Twitter recently?
I did. So it's a design pattern for turning events into materialized views, right?
Yeah.
In a nutshell, so you have the separation of concert, right?
Right. So what's the definition of it?
Maybe I will go through an example in here, because the definitions, as I said, it's a design pattern for turning events into materialized views, but it can be described using this, because I have, let's say I want to suspend my account.
Okay.
So
wait, you want to suspend your own account?
Yes.
Okay, sure.
So what I do, I send a command, suspend account, to my suspend account service or whatever it's called, right? And then the system is going to validate my command. Maybe it's going to accept that, or it's going to deny the command, right?
Because if you're already suspended, then you can't.
It doesn't make much sense to suspend that again, right? But let's assume the command was accepted, and I'm going to emit some series of events, which are going to update some materialized view in my database, right? And then this materialized view is going to power my account model used to do complex queries.
Right, so I can ask questions about the account, and the events are going to be event sourced to update the account model.
Yes,
Makes
so coming back to your example, this query side would answer a question, what's the speed of the boat at this certain point of time?
Yeah.
Does it make sense?
Yeah, so the command would be like, every time I encounter a knot, that's a command, and I shout that out, and then I aggregate it.
So, how do I do CQRS? And in a normal architecture, and a microservice architecture that uses Spring Boot, for instance. You are familiar with Spring Boot, right?
Yeah, used to be. I like Go now.
All right. I cannot say that because I'm Spring Developer Advocate.
That's right.
So we have this command service, which is backed by Spring Boot.
Yes.
And it's the one who's going to answer the question, hey, is this command going to be validated or not? I'm going to deny the answer, the command, or accept the command. If that happens, if the command is accepted, I'm going to throw an event, right? So the command, they generate events. And we keep them in our event store, right? But then you have this. So you have a set of event processors. Again, it can be independent Spring Boot application. And events are broadcasted to those event processors, right? So there are like tons of them. And what they can do is that they can translate a specific series of events into a materialized view. Let's say I'm going to answer to update a state in my MySQL database, right?
Yeah.
Why? Because then I need to answer a query, and this database powers my query service, which is yet third application Spring Boot backed.
Okay, wait. So let's say the command service then is one of those Portuguese sailors, and by command he's reeling in that log line. Then the event processor is another Portuguese sailor, and he's calling out the number. And then somebody else is from, the brain, that would be the query service. So that makes a lot of sense.
Yeah.
So that's how CQRS relates to event sourcing.
But I'm not saying they have to be like independent apps, you know?
Because that would be expensive.
That's your choice. They have different responsibilities. Okay. They have nice boundaries. You can keep them separately as independent apps, independently operated and deployed, but it's nothing wrong, I would say, to keep them together, right? So it's your choice.
Yeah, that would be cheaper. I'm not IBM. I can't afford to buy all this. Yeah.
The thing is that it's your choice after all.
Yeah.
And that's good because you have the choice. Yeah. You're not forced to do any of this. All right. So how does it apply to even a bigger picture? So there is a thing called API Gateway, which hides the implementation details from our end users, right? So let's say I would like my end user to operate only with front-end application. Again, Spring Boot backed, right? So it might be just series of HTML static files, right?
Right.
And then I'm going to delegate his actions or her actions to my API Gateway to, and then again, it turns to one of the places. It might be suspend account command, so I'm going to delegate to my command API. So to my command services. I'm going to validate the command or deny the command, and if the command was accepted, I'm going to throw in an event. The event will be picked up by one of the processors, again, Spring Boot application, and its job is to actually translate these events into some state in our data store. So, for instance, again, MySQL. And then MySQL powers up the query service, which is used for API Gateway to answer queries. Does it make sense so far?
Yeah, so I can ask questions and I can give commands, but I only have one API gateway to do that. So the front-end team, we hide all of the complexity and we shove it beneath the API gateway.
Yeah.
And so we essentially have one microservice here.
Yes, and there is, I mean, from the point of view of the client, yes. And there is this Spring Cloud Gateway project. Have you heard about that?
Yeah, I think so. It's reactive, I heard.
It fits nicely.
Yeah, good. I'll use that.
But it generates a problem.
What's the problem?
Because as an user, I would like to see an immediate effect of my action, right?
That makes a lot of sense. Yeah.
Or if I'm going to suspend an account, I would like to see, hey, account was suspended. If I take a look at the state of my account, just immediately. But here,
I order a shower head, I want to make sure that it comes to my house.
yeah, at a certain point of time.
Right.
So here, let's go back to our example with, I'm going to suspend an account. So hey, I'm going to throw a command, suspend account, to my command service, right? And then it's going to emit an event, account suspended, right? So the write API will emit an event, account suspended, this specific one with this contract number, and so on, et cetera, right? And yet, it takes time for the event processor to process the event and update the state.
Because it's eventually consistent.
It's eventually consistent.
Yeah.
Event processor processes events at its own pace, right?
Yeah.
So there is this time when the data might be stale. And I would like to see my own writes. That's actually a guarantee which is called read your own writes.
Right.
I would like to do that.
So if you have two APIs, you can't call them at the same time. Right?
Yeah. And if you are the same person who does writes and reads, you would like to see immediate effects.
Exactly.
If you are different persons, I think it's not a problem, but you as a person would like to see the effects of your own actions.
So how do we solve that?
So one of the tricks, there are several, but let's talk about one of them, would be, hey, if my command was accepted at the command level, right? Because I delegated to the write API, if the command was accepted, I know that my query side eventually will be updated, right?
Right.
So what I can do is actually play around with my front-end application and change the state of the view in there.
Because I'm given like a receipt, an acknowledgement of the state change, then I can just update the application.
I know it will happen at some point of time in the future, right?
Right.
So I know that the user is not going to, refresh the page during the next half a second, and then I don't need more time to process the event and update the materialized view, which is used to query the state of the account.
Yep.
Does that make sense?
That makes sense.
Cool.
All right. Rock and roll.
Cool.
Okay,
and now there is your reference architecture.
All right, so we'll
social
hand
media.
in. So I have a whole 12 minutes to go through this, which will be fun. So how do you do a friend of a friend query with microservices? Now this question will really rack your brain, because this very simple domain graph here, which is familiar to all of us, who knows what a social network is? You don't have to raise your hand. Now this is the domain graph for a social network. So a company like Facebook actually has a very difficult challenge if they have a distributed system where they store the relationships in one application and they store the users in another. Now, day one of building microservices looks like this. You get a lot of power. You feel like maybe Tony Stark or Wonder Woman. Basically, you're able to shoot the lasers out of your hand, but day two is a lot more difficult, right? Now, here's the architecture. I have a friend microservice and I have a user microservice. This is the design that our team came up with. Now, I have a small team of developers on each one of these applications, and the schema of the user service is going to be my users with their user details. And on the friend service, I'm going to store the connection between two users. And so the schema for that will be user 1 is column 1, user 2 is column 2, right? So I create a relationship. Now, commands are going to come in through the user service to maybe create a user or suspend a user or to add a friend. And when I want to add a friend, I'll call the friend service. So I can put an API gateway on top of this and do the CQRS thing. Now, what if somebody from the front-end team says, we need to build a recommendation query that will recommend which friends I should be friends with? Now, that's very difficult because let's say that Bridget, for instance, who doesn't have Facebook, decides to go on Facebook and and is friends with Joe. Right? And Joe has friends. Joe's on Facebook, and he has friends. And so we have to query Bridget's profile first, and then, we have to query, So we have to query Bridget's profile first, and let's say she's friends with Joe. That's one person. And let's say Joe has 10,000 friends, which is true.
It sounds like a recursive query.
Yeah, so then what we have to do is we have to call back from the user service to the friend service for each one of the 10,000 friends, and then we're going to have a huge data set. And then we have to do that again. So we basically get an exponential complexity here calling between these services. So in this architecture, you'll end up looking like this, because you won't really know what to do because you're going to bring the system down on its knees very quickly. And so there's a better way to do this. It's called materialized views, and this is the architecture that Jakub just explained. Now, what I'm going to do here is I'm going to put a message broker in between the user service and the friend service. And I'm going to create another application called an aggregate service. Now, an aggregate service is like a backend for front end. Who's heard of a BFF, backend for front end? Right? So that's exactly what it is. It's a read-only database, really. You don't want to put any business logic in it. What it's used for is to generate things like recommendations. Now, I can actually use something like Neo4j, which is a better solution than going across the network to run a machine learning algorithm that generates recommendations of who Bridget should be friends with. And so let's say that we add Bridget as a user, and then we call the friend service and we add Joe as her friend. Now, those events are going to be passed to that message broker, and the aggregate service is going to be our event processor, and it's going to join together the data. It's going to replicate it from all of the events just like a transaction log would, except we're doing this across the boundary of the network. So this CQRS pattern makes a lot of sense because what we can do is create one complete, consistent view of all of our data in a single database, and we can use that and query that much faster than we would going across the network. And so that's why you would do it. So just to review, you create an aggregated view from the event data, from the user service and the friend service. That's going to be aggregated in the aggregate service. And that's where our front-end developers are going to call the API for friend recommendation. They'll provide Bridget's user ID, and then it's going to find the friend recommendation based off of her friends and Joe's friends. And so we can use Neo4j for that. Now, there are two distinct kinds of microservices. There's domain services and there's aggregate services. That's the name that I give them because it makes sense. So domain services are microservices that own the system of record for a portion of the application's domain. And we want that to be pure, right? We want to use domain-driven design. We want to make sure that these aggregate objects aren't muddied by API calls like a friend recommendation. And so we don't want to create a recommendation service, really. We want to create an aggregate service, and we can call it the recommendation service, but it's not truly a write service. So it's going to produce an API contract for the domain data that it owns, and it produces events when the state of any of the domain data changes, right? As Jakub explained. Now, it also needs to maintain relationship integrity to domain data owned by other services. And so let's think about this. What happens when, let's say, Bridget decides to leave Facebook? Then we're going to need to sever all of her friend relationships, and so we have to send all those events back to the friend service. Now, there's the aggregate service, and this is where people get caught up. Now, when you get a distributed monolith, it's usually because you're not using aggregate services. You end up getting a dependency between all of these microservices where you have to change one service that causes a change on another service, and you have to deploy those at the same time. And so you've gotten worse than the monolith. Now you have to deploy multiple services. Now, the aggregate service here solves that problem. It subscribes to domain events emitted by separate domain services, and it maintains an ordered, immutable log of events that it receives, so it can always go back and replay events and generate the state of the system. You can also change the views, right? So you can make projections of that data as well, which is very, very useful. So you don't just have to have one of these aggregate services, you can have many of them, right? So you can use the ideals behind microservices to go faster. And then finally, performance. It's going to provide performant read access to complex views of domain data. So you don't have to do all of those joins across the network. So there's an open source example. We don't have time to You could walk through their code today because we have 5 minutes left, but I'm going to open that up. And it's on GitHub. And so if you just search for event sourcing microservices basics, or just go to my profile, which is Bastani, and I think we send these slides somewhere, so you'll be able to get that information.
And you have 76 stars. Way to go, my friend. Nice.
Yeah, I'm getting up there.
Cool.
I have some other examples too. So I do a lot of reference architectures. The first one I did was Spring Cloud microservice example. So if you are new to microservices, and this was kind of like a 102 course, you can look at my blog, which is at kennybastani.com, and you can look at some other examples. But for this example, it's going to be event sourcing basics. And you have all the code here. I have my aggregate service, which is going to have my recommendation. I have a discovery service. I have my API gateway, my friend service, and my user service.
So just for the record, the name aggregate doesn't have nothing to do with DDD concept and modeling concept and tactical patterns from DDD. It's a different thing, right?
I'm not sure. You're the DDD expert.
I have no idea. I think it's something different.
We should probably read the book, yeah. But no, the aggregate service, the idea of the aggregate service here, you would probably call that the recommendation service instead of the aggregate. But the abstract name of it, the conventional name of it would be, it's explained in the docs. Read the manual.
All right.
Yeah, so it's all here. And I think that is all that we have, and we have 4 minutes for questions. Does anybody have any questions?
No questions.
Okay, we have a question in the front. Bridget.
My question, and here's the big question, is if somebody thinks they want to get started with this, and they look at my Git repo, and there's a lot of stuff in there, what should they do first?
Read the manual.
Wait, we have to repeat the question. So, Bridget asked, what should we do first if we go to the repo here? So yeah, reading the manual is good, but you don't see usage on here. I need to add that. But there is a Docker Compose file here. And in this Docker Compose file, it's going to fully set up on your machine that architecture, and it's going to set it up in order, because this uses, I think, V2 of the Docker Compose manifest. And so it's going to bring in everything that you need from that architecture, and then you'll be able to look through the code itself if you understand Spring Boot, and you'll be able to see the event processors, you'll be able to see the controllers with the command API and the query API. If I had more time, I think I have 2 minutes, but I'd rather answer questions. It's all in here. So there was another question back here.
Yeah.
So we have to repeat the question. So if we have this immutable log of events, which immutable means you can't change them, how do you obscure the information and make it private inside of the log?
Yes.
Correct. Oh, right.
I have an answer for this. It's not mine. I read about this in Greg Young's book, which is about event sourcing, apparently. So what you can do is that you actually are not able to delete a log because it's an audit log, so you cannot touch this, but you still don't want this private data to be in there, right? So what you can do, and what is suggested in this book, is that you encrypt the private data with your private key, right? Every time there is a private data, you encrypt that, and you have this encrypted data in your private log, in your audit log, I'm sorry. And then if you need to really delete this information because that you are obligated by the law to do so, you just lose your private key. And that means the data is like untraceable. You cannot do anything with that. So that's one of the suggestions. There were many of those, at least 2. So at least 2.
I like that. It also adds a lot of overhead, especially in the programming model. But yeah, that's something actually we should bring back to the Spring team and talk about. Yeah. Very good question. Thank you. Another question?
Just one comment. You actually find the law, you cannot simply encrypt the data on the key because technically, in theory, if you reproduce the data and then compare against the result of the encryption, you can get the information. You can just check that the information is right.
All right. Sure. There was a second suggestion. All right. I don't remember the second option, but there was something. An actual.
Yeah, so you would actually store, okay, so how you would do this is you would store the ID in the log itself, and the ID would then relate back to a record stored in the actual data in a different store. And so then you would join those. Actually, that's how Apache Kafka works. So you have RockDB, which is an aggregate. So you don't have to actually store in the message the data. You can store IDs that point to data somewhere else, and then just delete the data, right?
So you can have like pointers, right, to different part of your data.
Yeah,
that's
I think
nice.
that probably sounds
that's good.
better, yeah. Because quantum computing is coming out, and that's going to break the encryption, right?
I think that was actually the second suggestion in this book. So thank you.
He read the book, I think.
You read the book, yes.
Oh,
Nice.
awesome. Congratulations. Wonderful.
Cool.
Okay, so I think that's all the time we have for today. I just wanted to say thank you very, very much for having us. And if you want to, I have another slide, one more slide. Okay, that's it. So if you want to take a photo of that, that has the name of the repository on it. So thank you very much for coming today. If you have any questions, I'll be up here on stage. Thank you.